Hello, I'm Warren Powell, and this is a talk I'm calling Learning While Doing. So, this is going to apply to problems where you're already doing something, you want to do it better, and I'm going to use the context of optimizing the cash on hand for a mutual fund. Now, uh, this is all boils down to this wonderful problem, well known to academics, called the newsvendor problem. It's a classic problem in operations research. We have to allocate a resource like newspapers to meet an unknown demand. And I have to juggle with what's called the overage and underage problem, because if I allocate too many newspapers, I'm going to have leftover newspapers at the end of the day. If I have too few, then I won't satisfy the market demands. Now, we start off with a little bit of math where I have to determine X, which is the number of newspapers to allocate, to meet this demand that I don't know at the time that I made the decision. Now, I have to find the X that maximizes the profits on average over all the various different demands. Now, this is a nice little exercise academics love to teach at universities. To find the optimal X, we take the derivative, set it equal to 0. If you don't understand this, don't worry. I can, with a little bit of algebra, I can find what we call the critical ratio, which tells me the probability that that I'm under the demand, okay? In other words, that I don't cover the demand. The optimal probability is the cost per newspaper C divided by the price that I sell it. Now, C is supposed to be less than P. As C gets close to P, that means the costs are very high, and I want to always sell all my newspapers. I don't want to ever have newspapers left over. Whereas if C is a very small number relative to price, which is usually the case with newspapers, I'm okay if I'm not covering a high percentage. Okay. Now, we academics love to teach this because it fits on a blackboard in a classroom. There's a very nice insight. Now, there was a student at a major business school that got his very expensive MBA. He was running a mutual fund, and then he sends his professor this email. Now, this is kind of a long email, so I'm going to make it a little bit shorter. Start off, Professor. The newsvendor inventory problem we learned in class looks like a way to optimize how much cash I should hold in the mutual fund. So he has a little description. Mutual funds hold a certain percentage of their assets in cash to meet the redemption requests. And we've got this overage underage thing that I described with the newspapers. If we have too much cash on hand, then I'm losing what I could earn in investments. But if I have too little, if a redemption request comes in, then I have to liquidate stocks. Now I've got the usual complications. So for example, there's correlations on the return on portfolio and requests. If the stock market isn't doing well, I tend to get a lot of requests for redemptions. I've also got two types of customers. I've got the retail investors. There's a large number of them. They make very small requests. And I have these institutional investors, much smaller number. But when they want to do redemptions, it's very, very large in the millions. And in fact, I have to wire them the money, whereas the retail investors, I can just put it in the mail. Now, so he looks at it and realizes that what he learned in class didn't really apply. So he's saying, gee, professor, I didn't seem to be able to solve this problem for my $70,000. Do you have any references that could help me do this? So what's happened is the student was taught this stylized problem, the newsvendor problem, which the professor solved in class. The problem is the student wasn't taught how to think about the problem in a way that allowed him to go after real-world problems and rise in practice. I call this a teaching failure. By the way, I have taught this material at Princeton for many years, and I have many friends who also teach this. This is a problem with the field. Now, I'm not going to just solve this one problem. I'm going to show you how to solve the problem in a way that I think applies to many operational settings. So we're going to go back to, here's my email. Now, we've got a hint of how to solve the problem right there in the email. Mutual funds hold a certain percentage of their assets in cash to meet redemption requests from investors. Now, let me point out that one of the concerns that the manager had was that this is not a newsvendor problem, and he's correct. It's not. It's an inventory problem, because if I have money left over at the end of one day, That's still held the next day. Now, why doesn't the professor solve the inventory problem? Well, because inventory problems are really hard. We like to do the news vendor problem because it's easy. So there's a lot of things going on. And the fact that it's actually an inventory problem and not a news vendor problem is almost the least of our worries. Now, what we're going to do is we're going to solve this by starting with their existing policy. So X is how much money that I have in cash, and I'm going to use a formula called a policy that says I'm going to take some number alpha, might be 0.1% or 0.5%, times the number of assets. Now that percentage, that alpha, is a number that I can tune either in a computer simulator or what we're going to do in this talk is we're going to do it in the real world. So what we're going to do is try to optimize that alpha asset. Now, let's imagine that I'm pretty sure that the number is somewhere between 0.1% and 0.7%, and I'm going to discretize it because you know what? If I'm within half of a tenth of a percent, I'm good with that. So what I have to do is pick which of these 7 numbers is best, but of course I have a lot of uncertainty about how well they perform. Now, one thing that can happen is that let's say that I try 0.7% and lo and enough, it performs well, it's higher than expected. I'm going to use that to update my belief about how well the 0.7%, but I have a beautiful property called correlated beliefs where that one observation is actually going to allow me to update all the other ones, mainly because it's continuous. So if 0.7% is higher than expected, well then 0.6% is going to be higher than expected and so on. Okay? Now, our challenge is to optimize the amount held in reserve. We don't have the resources to build a sophisticated model. So this probably describes most people listening to this from industry. We also doubt that we know how to replicate real-world conditions. So even if we had the resources, modeling the real-world conditions is not that easy. So we're going to use what I'm calling learning while doing. Okay? Now, we need a function. Now, it looks like capital A. It's actually capital alpha, but the capital alpha for Greek is A. This is a function called a policy. S is what I know, so it's my beliefs about everything. And what I'm going to do is I need a function, capital alpha, that is going to tell us what fraction between 0.1 and 0.7% of how many assets to hold in reserve. Now, it turns out that anytime I need a policy, any policy is going to come from one of 4 classes. Now, class 1, policy function approximations are simple rules. Class 2, cost function approximations are, I take a deterministic approximation and then parameterize it to make it work well. Value function approximations, if anybody's heard of Bellman's equation, that's where Bellman's equation is. Behind the scenes, you can set this up with Bellman's equation, you just can't solve it. Then the last is direct lookahead approximations. All of you have seen direct lookahead approximations. Google Maps uses it every day to plan into the future. Now, I'm only going to talk about 2 of these. These are the 2 that make the most sense for this problem, the CFAs and the VFAs. Now, we're going to start off by assuming that I have an estimate, maybe it's just subjective, of how well each of these fractions are going to work. I'm going to call that estimate mu bar for alpha. Now, alpha is always a number between, it's a discrete number from 0.1 to 0.7%. And so I had this initial belief mu bar. Now, I also have a distribution of belief because I'm not really sure how well these are, okay? So I've got that distribution of belief. You can do it as a bell-shaped curve. You can do it as plus or minus error bars. Now, I need a formula for telling me how to determine that alpha. And under the category of cost function approximation, the CFAs, here's 3 formulas that you can find all over the literature. They all have some things in common. First of all, they start off with your current belief. Okay, that's the foundation, is to say, give me your best estimate. Now, they also each have a way of estimating the uncertainty. So this is a measure of the spread. Now, they have a tunable parameter where what we're going to do is multiply that tunable parameter times the measure of the spread and then blend that in with my point estimate to get an index. Now, what we call my deterministic optimization is to simply take this index for each possible value of alpha, there's only 7 of them, and I have to find the best one. Well, okay, that's not a very complicated optimization problem, but it is. It's a sort, okay? So you have to compute this index for each of the 7 values, find the best one. So the challenge there is what's theta. Now, I have to pick which one of these policies. I'm going to tell you I've had a lot of success with this one called interval estimation. So let's run with this, okay? Now, I do want to just make sure we don't get lost in these parameters. So one thing is we're trying to tune the parameter alpha asset that determines the fraction of the assets under investment, and that's a number from 0.1 to 0.7%. So we have 7 possible values. Now my policy, my interval estimation policy, also has a tunable parameter, theta IE. That's the one that I multiply by the standard deviation, add it to the mean. Now that's going to be a number somewhere between 0 and 3. So think of it as I might go up 0 standard deviations, I might go up 1, 2, or 3 standard deviations. Now, if I go up 0 standard deviations, that's like saying I'm going to use my best estimate. I think 0.5% is right. I'm going to go with 0.5%. The problem with doing that is that maybe the 0.7% really is better. And maybe I tried it a couple times and it didn't work well. This is where we have to acknowledge that uncertainty might mean that 0.5% I may be overestimating it, and the 0.7% I may be underestimating it. And remember, I've got to do this for years and years and years, and there's a lot of money behind the scenes. Now, what if I do theta I equal to 2? That means go up 2 standard deviations. Now the 0.7% looks like it's best, okay? Okay, how do I go about finding this theta IE parameter? Now, first of all, I have to say, how do I evaluate? So let's say that I'm starting off, S0 is what I know. These are my initial estimates. And I'm going to take my initial estimates, I'm going to take my capital alpha policy that will say, okay, here's the best one. Maybe it's 0.5%, maybe it's 0.7%. I'm going to pick that allocation. Then I'm going to see how well I do, and I'm going to call that W. Now, W, that's my variable for capturing all the new information came in. How many deposits to get, how many withdrawals, what are the market returns, what are the interest rates, all the random stuff that I didn't know when I made my decision. Now, I'm going to do this day after day after day, and I'm going to keep doing this, learning how well I do along the lines. In the process, I'm also going to add up how well I did every day. How much money did I lose from the market by keeping it? How much did I lose for having to do sudden sales of stocks? And I'm going to add that all up, and that's how well my policy for testing alpha is working. Now, remember, we're evaluating the policy for choosing alpha. So alpha, day by day, I'm using my policy to try out different values of alpha. I'm not just trying the same value of alpha over and over again. I'm trying different values. I'm not evaluating a particular value of alpha. I'm evaluating the policy. Now, this is how well my policy did. Let's say I do that for a month, okay? And I sum up the results. This is how well my policy has done for some period of time, okay? Now, the policy pi consists of the function, which is alpha times assets, and then the choice of the parameter alpha, okay? So you first have to choose that it's some linear function, and we're just going to use the common sense of our mutual fund manager. Maybe if we hire somebody who does a PhD project and does some fancy algorithm, he'll come up with some other method for choosing how much, but we're just going to go with the simple practical method. It's just that we're going to tune it. Now, how do we tune? Well, one way to tune is in a simulator. I can build mathematical models and run a simulation. Now, there are 2 ways to generate the outcomes of these W's. That's all the redemptions and the deposits and the market returns. One is to just use backtesting, history. Now, the finance people do this a lot. They just go back in time and say, I'm just going to take history. Okay? And there's nothing wrong with that. You still have to build yourself a computer model. Now, another way, a little bit, well, actually quite a bit more complicated, is maybe I don't want to depend on history. I'm going to create it because history only gives me one sample path over the last, say, six months. Maybe I'm going to do fancy mathematical models to recreate history because that way I can then generate maybe 100 or 1,000 possible sample paths. But that's not the path that I'm going to do in this talk. I'm going to do this in the field. We're going to do what's called learning while doing, okay? Now, what we're going to do is we're going to take our policy, Now, one of the things I do have to struggle with is how do I pick that theta IE parameter? Okay. Now, what we're going to do is I do have to optimize that theta IE parameter. So, in other words, while I'm trying to find the best alpha, I have to actually also optimize my tunable parameter in my otherwise very simple policy. Now, taking advantage that we did program it up on a computer, and I had a very talented PhD student, he generated this graph. Now, this is an opportunity cost. Let me just say smaller is better. And if I set that theta IE parameter to 0, I get a very high opportunity cost. In other words, ignoring the uncertainty doesn't work well. You're not going to do well by simply taking your point estimates and say, well, that's what I think it is. I'm just not going to do any exploration. If you optimize the value, you do get a much better result. Okay, so optimizing this theta IE parameter is important, but it's also hard. So my basic policy, remember, I'm still going down the path of saying I'm not going to do something fancy. I'm just going to do what the mutual fund manager is already doing. I still have to do a good job of my policy for testing different values of alpha. Now, let's go back to my original problem and that original policy and say, is that actually the only policy that I can think of? So I started off by saying, well, let's just use whatever the mutual fund manager. But he was also very careful to say the behaviors of the retail investors and the behavior of the institutional investors are really quite different. Maybe I could do a different policy. Maybe the policy could be one factor alpha times the retail assets and a different alpha factor times the assets. Now I have a two-dimensional problem, and I have to find the best values of alpha over a two-dimensional surface. Okay, this is going to be harder. So now I have a two-dimensional surface. Here I've actually discretized a 50 by 50 grid, so instead of having 7 values, I have 2,500. But, all is not lost. Now, to find the right value of the combination of these two, I'm going to go to a different learning policy called the knowledge gradient. That was the second of the two policies that I talked about. Instead of the cost function approximation, I'm going to use what's called a direct lookahead. This is in the same class of policies as Google Maps, but this one's called the knowledge gradient. No math, I'm going to sketch through roughly how well this works. And the knowledge gradient was originally developed by one of my former PhD students, Peter Frazier. This is work, I'm reporting on work that was contributed to by two other graduate students, Ilya Ryzhov and Warren Scott. Now, I'm going to start off and say, okay, right now, my best belief is 0.5%. If I stop now, that's the one that I'm going to go with. Now, what if I try 0.6% and I get a performance that's a little bit better than I expected? Now, I use that little bit better than expected to update my belief. Now, I don't go all the way up to the dot because I do know that it's noisy, but I go up a bit, but it's still not better than the 0.5%. So in other words, when I compare the two beliefs, I still think 0.5% is the best. Now, what if I try 0.6% and I get a big bump up? And with that big bump up, and when I update my beliefs, now the 0.6% actually does look better than the 0.5%, and I now have an improvement. I did better. I now think the 0.6% is better. It means that I'm going to change my decision. So first of all, most important, because I think it's better, I'm changing my decision, which is critical. If I don't change my decision, I don't have a benefit. And how much it goes up is my best estimate of the benefit. Now, let's go back to here and now, I think 0.5%. I want to try one of the other ones. I don't know which one to try. Let's think about trying 0.6%, but I haven't jumped forward yet. I'm just thinking about it. And the outcome, I don't know what the outcome could be, but it could be any of these outcomes, okay? Could be worse, it could be better. But when I take any one of these possible outcomes and pull it together, I can say, well, there's a certain probability that the updated belief has no improvement. And there's a certain possibility the updated belief does have an improvement. Now, if I If I integrate over that, I have a certain probability of zero improvement, followed by different possibilities of some improvement. And when I average over those, that's the expected improvement. That's the knowledge gradient. Now, I haven't yet tried the 0.6%. I'm thinking of it. What I want to do is to get that knowledge gradient, not just of the 0.6%, but for all the other possible things that I might try. And if I have 2,500 possible combinations, I'll do it for all 2,500. The calculations aren't that hard. I can easily do it for all 2,500. Now, what I'm going to do here is, because I can easily do it for all 2,500, I'm going to give you an illustration of this search. Now, on the left-hand side here, this is my current estimate. I started off with just a flat surface, but this is the surface after I've done 4 experiments. Roughly, I've tried each of the 4 corners. Now, on the right-hand side is the knowledge gradient for each of the 2,500 points. Now, let's say I just did that point in the corner over there to the left. If I do a measurement at that point, the knowledge gradient drops. Because I have done a measurement at that point, the value of doing one more measurement, that's what the knowledge gradient is. It's the value of doing another measurement at each of those 2,500 points. Not only drops at the place where I did the measurement, but because of correlated beliefs, all the stuff nearby drops down as well. Because if you do something right at 0.1%, I have a pretty good idea what's going to happen at 0.2%. Now, I've updated my surface for all 2,500. Now, there's clearly a big flat spot there. But, if you go in with a computer, it'll find the best of all the ones. And there it is, the new optimum. It happens to be right there. It's incrementally better than everybody else. So that's the new one that I'm going to try. And if I try it, so first of all, the knowledge gradient dips down, because now that I've tried it at that point, trying it again or anywhere nearby is not a useful thing to do. Now, on the left-hand side, it says, yeah, I didn't learn anything. Surface didn't move anywhere. It's sort of a meh experiment. So what I'm going to do is go back to my knowledge gradient surface and find the new optimum. Well, there it is on that ridge. And I'm going to go try it, and I got a bit of a bump. Looks like I may have gotten lucky. Now, it looks like I should try other things in that region, but the knowledge gradient is saying not so fast. There's this other area here that, based on the uncertainty, would be more promising to try. That's my new optimum. Well, it turns out by trying it, that didn't work out that well. And now the knowledge gradient surface is starting to cluster around that point. In other words, after 9 experiments, now I had 2,500 points, but after 9 experiments, I've got a pretty good idea of where this optimum is. Now, remember, this is not inside some computer here. Where we're running this is in the field. And each of these experiments could be observing it from a single day, more likely trying at value of alpha and watching it for, say, a week is maybe the way that you would do these experiments. So you want this to move fairly quickly. Now, so let's go back to our graph of the opportunity cost. Now, when I do the opportunity cost for the knowledge gradient, here's what I get. First of all, it's very good. It's very low. In other words, it's a very high quality. Notice that it doesn't change with respect to theta, i.e., knowledge gradient doesn't have a tunable parameter. So it's a more sophisticated policy. You have to do a little bit more work. There are simple versions of the knowledge gradient that can be done in a spreadsheet. There's a little bit more sophisticated version that takes advantage of this behavior called correlated beliefs. But it's a consistently good policy, and it doesn't have a tunable parameter. So the thing is, the original interval estimation policy, a form of CFA, is a very simple policy, easy to code in a spreadsheet, but you've got that crazy tunable parameter. And most people, what they do is they don't really optimize that parameter. They take a best guess. This presentation should be making the point that says, okay, well, you really do have to guess at it pretty well. Okay. Now, what I found surprising, this was a very astonishing result from the research, was that at the end of the day, interval estimation ended up winning, but only if you really tune that tunable parameter. Okay. So what we've got here is two policies. One very simple, that's sort of a basic rule that says, hey, maybe just pick one standard deviation up. So if you pick, I'm just going to go up one standard deviation. If you look at the opportunity cost, you can see that that is not as good as knowledge gradient, but it's not terrible. Okay, in other words, sure, maybe it's worth something. Um, we were actually very surprised that interval estimation did end up winning if it was perfectly tuned. Probably in real world, you can't really do that tuning as perfectly as we were able to do in our experiment. Now, final notes: learning while doing. It's a powerful way to improve operational processes that are already running in the field. Notice that you don't need a mathematical model. You don't need a fancy computer algorithm. You don't need to model all the complicated stochastics because you're going to live them. It does require that you understand that your decision of how much, that percentage of the assets is a decision, and how you make that decision is with a method that's called a policy. And of course, you'd like the best policy. Now, doing the trial and error on alpha, the alpha times the number of assets is a policy for making the decision. Picking alpha is also a decision that needs its own policy. Now, there's two classes of policies. Absolutely appreciate that everybody likes simple, but I will end with the consistent message: the price of simplicity is tunable parameters, and tuning is hard. So I'd like to thank everybody. This is a sequential decision problem. I've got a whole web page on sequential decision analytics. If anybody would like a copy of these slides, you're welcome to use it, even in your lectures and whatnot. But email me at wbpal328@gmail.com. Thank you very much.